the allosphere. It's a 3-story metal sphere in an echo-free chamber. Think of the allosphere as a large, dynamically varying digital microscope that's connected to a supercomputer. 20 researchers can stand on a bridge suspended inside of the sphere and be completely immersed in their data. Imagine if a team of physicists could stand inside of an atom and watch and hear electrons spin. Imagine if a group of sculptors could be inside of a lattice of atoms and sculpt with their material. Imagine if a team of surgeons could fly into the brain as though it was a world and see tissues as landscapes and hear blood density levels as music. This is some of the research that you're going to see that we're undertaking at the allosphere. But first, a little bit about this group of artists, scientists, and engineers that are working together. I'm a composer, orchestrally trained, and the inventor of the allosphere. With my visual artist colleagues, we map complex mathematical algorithms that unfold in time and space, visually and sonically. Our scientist colleagues are finding new patterns in the information, and our engineering colleagues are making one of the largest dynamically varying computers in the world for this kind of data exploration. I'm going to fly you into 5 research projects in the allosphere that are going to take you from biological macroscopic data all the way down to electron spin. This first project is called the allobrain, and it's our attempt to quantify beauty by finding which regions of the brain are interactive while witnessing something beautiful. You're flying through the cortex of my colleague's brain. Our narrative here is real fMRI data that's mapped visually and sonically. The brain now a world that we can fly through and interact with. You see 12 intelligent computer agents, the little rectangles that are flying in the brain with you. They're mining blood density levels, and they're reporting them back to you sonically. Higher density levels mean more activity in that point of the brain. They're actually singing these densities to you with higher pitches mapped to higher densities. We're now going to move from real biological data to biogenerative algorithms that create artificial nature in our next artistic and scientific installation. In this artistic and scientific installation, biogenerative algorithms are helping us to understand self-generation and growth, very important for simulation in the nanoscaled scientists. For artists, we're making new worlds that we can uncover and explore. These generative algorithms grow over time, and they interact and communicate as a swarm of insects. Our researchers are interacting with this data by injecting bacterial code, which are computer programs that allow these creatures to grow over time. We're going to move now from the biological and the macroscopic world down into the atomic world as we fly into a lattice of atoms. This is real AFM, atomic force microscope data from my colleagues in the Solid State Lighting and Energy Center. They've discovered a new bond, a new material for transparent solar cells. We're flying through 2,000 lattice of atoms, oxygen, hydrogen, and zinc. You view the bond in the triangle. It's 4 blue zinc atoms bonding with 1 white hydrogen atom. You see the electron flow with the streamlines we as artists have generated for the scientists. This is allowing them to find the bonding nodes in any lattice of atoms. We think it makes a beautiful structural art. The sound that you're hearing are the actual emission spectrums of these atoms. We've mapped them into the audio domain, so they're singing to you. Oxygen, hydrogen, and zinc have their own signature. We're going to actually move even further down as we go from this lattice of atoms to 1 single hydrogen atom. We're working with our physicist colleagues that have given us the mathematical calculations of the n-dimensional Schrödinger equation in time. What you're seeing here right now is a superposition of an electron in the lower 3 orbitals of a hydrogen atom. You're actually hearing and seeing the electron flow with the lines. The white dots are the probability wave that will show you where the electron is at any given point of time and space in this particular 3-orbital configuration. In a minute, we're going to move to a 2-orbital configuration, and you're going to notice a pulsing, and you're going to hear an undulation between the sound. This is actually a light emitter. As the sound starts to pulse and contract, our physicists can tell when a photon is going to be emitted. They're starting to find new mathematical structures in these calculations, and they're understanding more about quantum mathematics. We're going to move even further down, and go to one single electron spin. And this will be the final project that I show you. Our colleagues in the Center for Quantum Computation and Spintronics are actually measuring with their lasers decoherence in a single electron spin. We've taken this information and we've made a mathematical model out of it. You're actually seeing and hearing quantum information flow. This is very important for the next step in simulating quantum computers and information technology. So these brief examples that I've shown you give you an idea of the kind of works that we're doing at the University of California, Santa Barbara to bring together arts, science, and engineering into a new age of math, science, and art. We hope that all of you will come to see the Allosphere, inspire us to think of new ways that we can use this unique instrument that we've created at Santa Barbara. Thank you very much.